How do we start this? Okay, so it gives me great pleasure to present some of the work that we have done in the activity working group, and this is very much a team effort. And I'd like to acknowledge Aiden for donating a few slides also for this presentation. So it is not that we don't know that physical activity is good for you. So this is a recent study showing that the more activity you do, the slower you will go to your death. So it is a pretty firmly established risk factor. So that is not why we have done this in Biobank. But of course, it is completely impossible to translate this result here to public health action, because you would need to translate the inactive label to moderately inactive. Now, whilst we can try and do some calibration to fix this issue with a study that had compared these exposure measurements to objective data, there is no statistical magic that will fix the fundamental issues of self-report, which is that it is really difficult to ask 5 questions and make sure we cover all your life, even over Christmas. So that is the reason why we must enter, and have indeed entered with Biobank, a new era for physical activity epidemiology. We started in the 50s, in fact, with the London bus drivers, and we're now at this stage where we can study detailed exposure of physical activity so we can get to dose-response relationships with rare disease outcomes. That is why we have done that. And indeed, we have to do this, of course, at scale that is feasible, and we heard from the participants that this was a well-accepted method. So we stuck an accelerometer on the wrist. It has never been done before, and certainly never been done before at this scale, and most people thought we were bonkers. But even in 1973, which is why this slide or this picture is depicted, Jerry Morris, who did that originally, the original study on the London busmen, noted that sticking an accelerometer on people was a really good idea. So we followed the success formula of general biobank enhancements, which is to define the scientific need and then try and undertake the measurements, and then set down a working group that could derive summary information, put it back in the resource so that other people could use it for their research. That is the general structure of biobank enhancement working groups. So what is this signal that we have collected? It is very, very raw. We collect 100 samples in 3 axes every second, over a week, so we get an awful lot of data. This particular signal contains fundamentally 3 components. The activity component, of course, which is the focus of this talk, but it also contains gravity, and it also contains a noise component. Generally, we filter the noise out, and I'm not going to talk too much about that. But we will use the gravity for something completely clever, because we need to make sure that we reference our activity to gravity. So it wasn't a small feat, as you can imagine. Nothing is really in this study. About half of the cohort was invited. Half of those, a little bit less than half of those, agreed to wear the device, and almost everybody actually returned their device with data in them. So we had over 100,000 records to process so that we could derive summary measures of activity. We follow a general inference scheme, so we have the raw data that is available in the resource. If you disagree with any of these decisions that the working group has made, you can go back to that raw data and revisit any of these decisions. But these are the ones that we have made, and I hope to convince you that they are at least quite valuable for quite a range of questions. We go through some post-processing, mostly to reference the signal to gravity and to scan the record for when the participants have taken off the device. So, what is this gravity business? The monitor is uncalibrated when it comes out of the factory, and this was to make it cheaper. So that process would have made it probably twice as expensive to do this. So, but fortunately for us, we are sitting on one big calibrator. So we can take the segments in the record where the monitor is still and then we can reference that to gravity. So in this particular example, you would see that the z-axis is slightly offset, so we take that data and we shift it up a little bit, so that on this sphere, if you imagine a football that is 1g in radius, we shift the data so that it conforms to this particular construct. And when we're interested in activity, we do this first, and then we chuck away gravity. So I'm just going to convince you that this was a worthwhile effort, because when we chucked away gravity to get to activity, these are the means uncalibrated and the means uncalibrated in a range of studies that have used similar technology. And as you can see here, they shift by quite a margin, 10% in the UK and up to 100% error actually on the Brazil sample here. And this is just a test bed of why this was important. So it's not just a geeky little trick to become important. It was extremely important. We would have flooded the showcase results with error-prone data if we had not done this. So that was one of the decisions that we made. Another important decision is to scan the record for when people might have taken off the device. The protocol was they were supposed to wear it at all times, but occasionally people take it off, and we have to account for that. So in this particular record, you would see that maybe this person took the device off there towards the end. So in general, the participants at Biobank was extremely compliant. They did wear the device, and that enables us to use their own data to come up with a better, less error-prone summary estimate of their overall activity. So this is a little bit of a difficult slide, but we simulated different patterns of missingness. And what we could have done, we could just have chucked all that non-wear data away and taken a straightforward average, but we did not do that. We allowed the 24 hours in the day to be weighted equally. So now we get a representative profile of a person's complete day. So that was one of the tricks that we played to get the summary estimates here. And if you look at this graph here, different degrees of serious missingness, you would see that the naive estimates, which is those blue bars there, have higher error bars, a higher bias than our approach, which is the diurnally adjusted, as we call it, estimate. So in general, we were able to reduce error by threefold by this little trick. We also had some evidence of the validity of this particular approach. So all of these decisions summed up, and we had a little bit of data from Swedish women, as it were, comparing to a very, very accurate measure of energy expenditure. We've obviously measured movement, but we had a little small data set here comparing to isotopic assessments. And reasonable correlations, actually, 0.6, so about 36% explained variance. We also had access to a large UK cohort of similar age who wore a combined sensor, combined heart rate and movement sensor, individually calibrated. Again, similar correlations were seen. And these studies used predominantly the non-dominant risk. Biobank used the dominant risk. So we compared the two risks. You'll be pleased to know that actually they are fairly comparable. So left and the right hand are often doing the same thing. I will skip that one. And we are starting to conduct some UK-based research also on the isotopic comparisons. And I have to say, this is almost too good to be true. So this is the first 16 out of 100 assessments in the UK, age-matched to the UK biobank sample, and a rather encouraging explained variance of 80% of this particular summary measure. A couple of results just to give you a flavor of what you can do with this. So we can, of course, describe the age gradient by which people's activity levels differ. So this is a classic epidemiological observation of that we get, obviously, a little bit less active as we age. There isn't actually a great deal of difference between men and women, and we often see that with movement sensors. It's not quite the same for energy expenditure, but we often do see this actually for movement sensors. This is the diurnal profile of the cohort, and you will see that the age difference really just manifests towards the latter part of the day. So people tend, on average, to get up at around the same time and be active, and then we tail off a little bit more as we get older. So those were volume measures. We have also put continuous measures of intensity into the resource. And this is a cumulative frequency of the time spent above a certain movement intensity level. It is a little bit difficult to interpret that, so I've related it here to BMI classification, and as you can see on the right here, the time spent above a certain activity level here is highly inversely related to your BMI class. So I would encourage you to use this resource, and with that I'd like to thank my fellow activity group members. And if you're interested in doing further work, we are setting up other working groups with a specific focus of deriving extra exposure measures to further enhance the resource. Thank you.